Good morning. So before we continue, I would like to ask if you have some questions, and if you received the files which I have sent to you concerning the material of the last lectures.
Yes, sir, we have received that. Thank you.
Okay. Any questions? Okay, if you don't have questions, then we continue. So what we have done in the last lecture, we have introduced the S matrix of quantum electrodynamics. And we have discussed the most important ingredients which are needed for its computation. This includes, in first turn, the decomposition of the spinor fields and electromagnetic field in terms of creation annihilation operators. Also, the expressions for the propagators of spinor particles, which are electrons and positrons, and also the propagator for electromagnetic field. We also discussed the construction of asymptotic states, which are in fact the states in the standard Fock space, where these states are obtained by applying creation annihilation operators of electrons and positrons and creation operator of photons to a vacuum state. And now our goal is to implement all these ingredients for a practical computation of actual scattering processes in quantum electrodynamics. Of course, there is a variety of processes which are physically interested, but today we discuss one of them, namely the Compton scattering. So let me start with this. As we have seen, the S matrix of quantum electrodynamics, SQED, is given by a time-ordered exponential of interaction term in the Lagrangian, which is d for x, psi bar gamma mu psi, a current, fermionic current, interacting with electromagnetic field, and this operator is normal ordered. Now, the process which I'm going to discuss is Compton scattering. Compton scattering. And in terms of physical particles, it consists in interaction of an electron with a photon. So gamma is a photon, E minus is an electron, into electron and another photon. So this is what Compton scattering is. Now, classically, scattering of light by an electric charge is a process known as Thomson scattering. So classically, the same process is called Thomson scattering. I already briefly described it last time, but let me repeat. So basically, you have an electric charge, and then you have electromagnetic wave, which interacts with this charge. And as a result of this interaction, the electric charge starts to oscillate, start to move, and it moves with acceleration. As any accelerated charge, it starts to emit radiation. It starts to radiate. And this effect is called Thomson scattering. This is a twofold process. First, action of the electromagnetic wave on the charge, and then radiation produced by the charge. As a result, the amplitude for the scattered light is proportional to the square of the electric charge. So it goes like E squared, where E is an electric charge, charge of electron. Now, This process in quantum electrodynamics is called Compton Scattering, and at leading order in the coupling constant, at leading order in not in the coupling constant, sorry, in H bar, this reduces to the Thomson scattering, but then it has high corrections due to the quantum effects. And now we are going to compute it in an explicit way. In particular, we want to define and compute explicitly the cross section for this process, applying all the knowledge which we can gain, which we gained in the previous lectures. So let's start from a situation where in the initial state we have just an electron with momentum p1. So that would be initial state. P1 is the momentum of electron. And photon. And we have a photon with momentum q1. And so this would be our initial state of electron and the photon. And then in the final state, we're supposed to find an electron and the photon with momentum p2 and q2. So p2 is the momentum of an electron after scattering, and q2 is the momentum of a photon after scattering. Now, at leading order of perturbation theory, the matrix element of the S matrix, I denoted by letter M, is given by the following expression. So minus g squared over 2, p2, q2. This is our out state. Integral d for x, d for y. T-ordered product of interaction Lagrangian, psi bar, gamma mu, psi a mu, depending on the point x. Fermions are also depend on x, so the whole composite object depends on the point x. And then another interaction term, psi bar, it's right, gamma nu psi, a nu depending on the point y. And then we close this with the initial state P1, Q1. So this is a matrix element of the S matrix, the one which I have written down here. At the leading order of perturbation theory, and the leading order here is G squared. The order G does not contribute because in this case, if you just consider the leading order, the first order in this expansion, which is proportional to G, you will see that it produces zero contribution because the number of creation annihilation operators which stand in the interaction term does not fit the number of creation operators or number annihilation operators in the initial and the final state respectively. So this means that in order to obtain the leading effect, you need to get down the interaction term in the exponential twice. And that's exactly what you see here. So this is the first time it gets out of the exponential, and this is the second time it gets out. And so at order G squared, you get this expression. Minus sign is here because of I coming down twice. G squared is there, and 2 is just 2 factorial, which comes out from exponential. No anti-ordered product here, you see it's inherited from the definition of the S matrix. Is this formula clear to you? That is a starting point. That is how it should be computed.
Yes, it's clear.
So if you want more orders of perturbation theory, you just need to take more powers of interaction term down, to take more powers down, and then in principle to repeat the same computation as I will be doing now. Then how to proceed? We know that to compute the thing, we first have to transform the T-ordered product time ordered product of our interaction terms into the normal ordered product. And of course, we do it with the help of the weak theorem. So I have to write T ordered product of psi bar x gamma mu psi on x a mu on x with psi bar gamma nu psi. Let's write everything here on y like this. A nu on y. This is, according to the weak theorem, will be given by the normal ordered product of these terms. First, without pairings. Let's do this in the following way. So since fermions can pair only with fermions, maybe I even don't need here for the moment to write electromagnetic potential. So I leave just fermions because they can pair only between themselves, among themselves. So let's not involve for the moment electromagnetic field. And then what you get here is psi bar gamma mu psi on x, psi bar y gamma nu psi on y. So this is the first term without pairings. Then there will be two terms where you have one pairing, and you will have two such terms. So first of all, there is a pairing between psi and psi bar like this, and the other psi bar and psi remain unpaired, plus another pairing, psi bar x gamma mu psi on x, psi bar on y gamma nu psi on y, where you pair this fermion with this one.
Professor?
Yeah.
So, but shouldn't there be a pairing between xi and a mu?
Between what? Between psi and
Xi
psi?
and, yes, and electromagnetic field?
Pairing between electromagnetic field and the fermion is absent. There is no propagator, so.
But they interact, right? So,
they do interact, but they do interact through this term here. This is what is interaction term. But there is no propagator between psi and a mu. This pairing is equal to 0. They depend on different oscillators. So if you compute vacuum expectation value of the T-ordered product, these fields do not talk to each other in a sense of having a propagator. I mean, fermion cannot propagate into a photon directly. The interaction of electrons and fermions is described exactly by these matrix elements which we are going to compute. Okay?
okay. Yeah.
And psi with psi is 0. You remember, psi with psi, psi bar with psi bar is pairing is 0. But I have not finished yet with the pairings because there is one more term where you have a double pairing. So psi bar x gamma mu psi on x, psi bar on y gamma nu psi on y, and then you pair these fields, and then you pair these fields as well. So this is term with complete pairings, so all fields are paired. And so this term is just a function of x and y, so it's not an operator anymore. And when we look at all these terms which we get through the weak theorem, we realize that the first term, I mean this one here, it contains too many electron creation and annihilation operators to fit the asymptotic states between which this operator is sandwiched, and therefore this does not contribute to the amplitudes, to the amplitude we are interested in. And so this term can be just omitted. It does not contribute to the scattering process we are interested in. The last term, as I said, is just a C number. So it's not an operator. And it also will not contribute to the connected path of the scattering amplitude. So this term also omitted for this reason. Why? Because if this is just a number, you can take it away, and then in fact you will get a pairing directly between initial and the final states, which just lead to the conservation of the initial momentum of the fermion. So P1 must be equal to P2, which means that the electron freely propagates and does not see photon. So this term is not also interested for this reason. So throwing away, we are left just with two terms. And we know what these pairings are, because we know that each of these pairings is just a Feynman propagator. And so if you continue, then the first term produced for you psi bar x gamma mu fermion propagator x minus y gamma nu psi on y normal ordered product plus, and second term gives you psi bar on y. This is what will be left over. Gamma nu s on y minus x gamma mu psi on x. So how to get these formulas? You need to accurately write the corresponding expressions in indices. So restore the indices of fermions, and then use the propagators for the fermion fields, which we have introduced in the previous lecture. In indices, just let me remind, it looks like psi I on x, psi bar j on y. Pairing is given by Sij y minus x minus y. And if you pair psi bar with psi j on y, then this is minus Sji y minus x. So you should be careful with indices and with the fact that fermionic creation annihilation operators, creation operators and annihilation operators anti-commute, and then this is an expression which you get if you then suppress finally upon you do this computation the indices. Then this is the expression which you will have. So this means that this S y minus x, or this S x minus y, is a matrix, and this matrix is sandwiched in between gamma matrices, and then it multiplies the column, which is this psi on x, and this from the left it's multiplied by rho, which is this psi bar on y, and the same with the first term. So this is an expression we have now to substitute in our amplitude, and we get the following. So what is left over is double integration over dx and dy. Then you have also electromagnetic field, which I'm of course not forgetting. I remember about it. A mu on x, a nu on y. But again, for electromagnetic fields, we do not need to take a propagator, because if you take a propagator, again, it gives us a C number, so not an operator. This C number can be taken away, and then you will get a pairing of asymptotic photons, which simply leads to the statement that momentum Q2 is equal to Q1. So this means that photon does not scatter. And so this contribution again will be a contribution into the disconnected part of the amplitude, which we are not interested in. And it means that photon freely propagates and does not see electron. Cross the contribution we have just found. So P2, electron state on the left, and then psi bar on X, gamma mu S X minus Y, gamma nu psi on Y, like this, plus psi bar on Y, gamma nu S Y minus X, gamma mu psi X. Okay, so this is what we have. Now, what is interesting is that if we now take the second term, this one, and make a substitution X for Y and Y for X, then this second term will become equal to the first one. And so what happens is a doubling of the first term. So effectively, this becomes simply minus G squared, double integral. Let's start from photons P2. Let's start from fermions psi bar X, gamma mu S on X minus Y, gamma nu psi on Y, P1, and then Q2, A mu on X, A nu on Y, Q1. So this is what we have to compute. Now let's assume that our electrons are polarized with polarizations S1 and S2. So let S1 and S2 will be electron polarizations. Electron polarizations. And the fact that we consider scattering of electrons, so we don't involve positrons, then in these expressions for psi and psi bar, we have to leave only electron creation annihilation operators. So only electron creation annihilation operators will be contributing to operators psi and psi bar. So we can just throw away the positron creation annihilation operators. And therefore, in order to proceed, we have first to compute the following matrix element. So P2, psi on X, gamma mu, S on X minus Y, gamma nu, psi on Y. So what we have to do now is to substitute here the expressions for psi and psi bar via creation and annihilation operators. And we also have to substitute the asymptotic states corresponding to electron in the initial state with momentum P1 and polarization S1, and an electron in the out state with a momentum P2 and polarization S2. And now when I substitute these electron operators, I will get two integrals. So integrals of the momentum K1, three-dimensional momentum K1, our standard normalization prefactors over K2, 3/2. Then there will be prefactor also coming from expansion of these fields psi and psi bar in terms of creation annihilation operators, or the same is also for the factors depending on K1 and K2 in the denominator, so omega on K1, omega on K2. Then there is a prefactor which comes from normalization of external states. Remember, so our external states are normalized in a relativistic invariant way. So this is prefactor related to that. And then we have the following: 0, BS2, P2, annihilation operator of an electron, B plus R1 on K1, creation operator of electron which comes from psi bar, then BR2 on K2, which is annihilation operator coming from psi, and finally a B dega S1 depending on P1 and acting on the vacuum. So this is external state, external in state, and this is out state. State. And then this we have to multiply by our spinors, which encode the information which come together with creation annihilation operators coming from psi bar and psi. So this is psi R1 on K1. And then we have this combination gamma mu S X minus Y gamma nu, and another spinor UR on K2. And I recall that these spinors, psi bar and psi, they are solution of the Dirac equation, which provide a basis for the decomposition of our field psi and psi bar in terms of creation annihilation operators. And on the top, of course, we have the exponentials AK1x minus IK2y. Again, coming from this expansion of psi and psi bar in terms of oscillators. Okay, so this is matrix element which we have to compute first. Any questions here? Is it clear where I have taken this expression?
Professor, here we have assumed by R1, R2.
There is a summation over this R1 and R2. We are summing over these indices.
Okay, perfect.
So R1 and R2 are two possible polarizations of an electron. Yes, remember that when we classified solutions of the Dirac equations, we classify them by the energy, so solutions with positive and negative energy. And then we classify solutions by helicity, helicity +1 and helicity -1. And these helicities are, I'm calling here in this context, polarizations. So R1 and R2 are running over values 1 and 2. And in quantum theory, you know, solutions with negative energy, we interpret it as antiparticles. But here, everything what is inside this matrix element is related to electrons, because we did not excite positrons. And that's why you see here only creation and annihilation operators of electrons. What can we do with this expression? What can we do with this expression? We can actually integrate, I think, over K1 and K2. But first we have to compute the matrix element which correspond to this creation annihilation operator sandwiched in between vacuum state. So what we do, we move B to the vacuum so that B will annihilate it. And then we also move B dagger to the right, to the left, to the vacuum to annihilate it. And since B and B dagger anti-commute to H bar, this will produce this will leave behind a certain contribution, and you know, also the anti-commutator of B and B dagger will be proportional to a delta function. Say when you do it for these two operators, you will get a delta function P1 minus K2, P1 minus K2. And this delta function allows then to perform integration over K2. And analogously, if you look at these terms and you exchange B and B dagger, you will be left with a delta function P2 minus K1, which allow you to perform integration over K1. So if you do these two integrations, then you will obtain the following answer.
Professor?
Yeah.
Shouldn't we also multiply by, like, example, 1/4 for 2 spin?
By what? Say it again. By
because our electron has spin polarization. So shouldn't we divide, like, for example, by 1/4 for here?
No, because I'm considering here the scattering of polarized electrons. So this S1 and S2 are considered to be fixed for the moment. So like S1 is 1 and say S2 is 2. For instance, helicity of the first electron in the in state is S1, which can be 1 or 2. And helicity of electron in the out state is S2, which can also be either 1 or 2, positive or negative. But we fix these helicities. Now, these helicities, which are labeled by R1 and R2, they are considered as being summation variables because over them we sum. So this means that when I will be commuting this, anti-commuting these oscillators, there will arise also Kroneckers, delta R1 S2 and delta S1 R2. And so these summation indices R1 and R2 will be replaced by S2 and S1 respectively. And that is why I see that upon I perform this anti-commutation, this matrix element, and taking the integrals over K1 and K2, this matrix element gets down. So these factors of 2 pi cube will cancel. And this matrix element gets down to the following expression. There will be a factor of 2 coming out, mc squared over h bar. And then you see omegas will cancel because now K1 and K2 will be replaced by external momenta, P2 and P1. And so omegas will go away. And what then will be left over? What will be left over is the following expression. U bar S2, as I said, R1 will be replaced by S2 on P2. K1 is replaced by P2, gamma mu Sx minus Y, gamma nu U S1 P1, exponential I K1 becomes P2 X minus I P1 Y. Yeah. Is it okay?
Excuse me, sir, where does this 2 comes from, the first number?
2, where does 2 comes from? Let's see. There is another 2 which I missed, sorry, here. 2 omega on P1, 2 omega P2. Yeah, that's what sorry, I have not written it down. So square root of 2 gives 2. And this is this 2 here.
Okay.
Thank you for the question. Yeah, this comes from normalization of external states. This upper square root is normalization, Lorentz invariant normalization of external states, or asymptotic states, as we call them. So this is the matrix element. It looks reasonable, reasonably simple. And now we can plug it into our integrals. But before, let me maybe also discuss this photon part, which involves electromagnetic potentials. We also have decomposition in terms of creation annihilation operators. So if I wanted to compute explicitly this matrix element of electromagnetic potential sandwich in between initial and outgoing photons, then I will get the following. So now I substitute expansion of electromagnetic field. That becomes a bit complicated because here we have to take into account all creation annihilation operators, which is inside a mu. And let's do that. So again, there will be two integrals. Then again, from the normalization of external photons, we get the factors 2 omega q1 to omega on q2. And from photons themselves, we get twice omega on k1, twice on omega on k2. Okay, so that comes from a mu and a nu. And now this is multiplied by the following matrix element. So vacuum, I create the photons with polarization, say M2 on Q2. This is outgoing photon. Then there is a creation operator from a mu R1 depending on K1. Another annihilation operator from another A on R2 K2, like this. And then creation operator for in photon depending on Q1 with polarization M1 acting on the vacuum. But this is not the end of the story because, as I said, yeah, so this I need to multiply with polarization Vierbeins, epsilon mu R1. Summation of R1 is assumed depending on K1 and another one R2 mu on K2, like this. And then there is a exponential term ik1x minus ik2y. But this is not the end of the story because there is another term here which looks similar. So 0 am2 q2. And here you will get a plus on R2 K2. A on R1 on K1. Then A 1, 2, 3, 4 external state oscillator Q1 acting on the vacuum. And finally, what I will have also polarizations. Polarization vectors. They are epsilon nu on R2 K2, epsilon mu R1 K1, and then ik2x minus, no, here there will be y now. K2 comes with y, and minus I k k1x. Then the bracket, I guess, is closed. Okay. Right, so this is what we have. Now we perform the same procedure as we did before. We need to commute A plus to the left here and A through A plus to the right. Analogously, we do the same A plus to the left and this A to the right. And in these commutations, we will be obtaining the delta functions, which allow us to perform later integrations over K1 and K2. And we also get delta chronicas, which make these photon polarizations R1 and R2, which over which we sum, to become equal to either M1 or M2. And so at the end, what will be left over after this integration, we will be left over with polarizations, where the synthesis R1 and R2 will be replaced by M1 and M2. Exponentials will be left over with K's replaced by P's. And then these terms, square roots of omega in the numerator and denominator will cancel. So if you do this accurately, then you will obtain the following. You will get epsilon mu M2 on Q2, like this, epsilon mu on M1 Q1, exponential I Q2x minus I Q1y plus epsilon nu M2 on Q2, M1 mu Q1, and another exponential. Okay, that is what you will have here. That is what you will have here. Mm-hmm. Now you can combine everything. By everything, I mean combining this matrix element of 4 fermions and this matrix element which comes from photons. And so combining, then we get M to be equal to minus G squared, Kaplan constant, 2C squared, MC over H bar. So this C will be combined with the powers MC squared, C squared, which we have here. And so we write this as 2C squared, and then MC over H bar is our sort of rigid combination, which is inverse Compton wavelengths, as we call it. Yeah, so maybe I write intermediate expression first, namely double integral d for x and d for y, then contribution from fermions on P2, gamma mu s x minus y gamma nu, US1 on P1, and then contribution of photon polarizations, epsilon, as I write them this way, mu M2 Q2, epsilon nu M1 Q1, exponential, I P1 plus P2 plus Q2 multiplied by X minus I P1 plus Q1 multiplied by Y, and plus exponential M2, not exponential, sorry, epsilon mu2 nu Q2, epsilon M1 mu Q1, I P2 minus Q1, X minus I P1 minus P2 Y. Yeah, this is what we get. So this comes from photons. And so this is photon contribution, and this comes from electrons. And what we need now to do is to perform this integration over X and Y. And this can be done efficiently in the following way. So you see that the fermion propagator here depends on the difference, X minus Y. That's why it makes sense to introduce the change of variables. So you will be integrating instead of X and Y over the difference X minus Y. So introduce like variable xi equals to X minus Y. And then you can take another variable eta to be X plus Y, for instance. After that, your propagator will depend on this variable xi. And then also in the exponentials, you substitute X and Y for xi and eta. And then you see that you can perform integration over xi and over eta in a very efficient way, because integration over xi will just produce you the Fourier image of the fermion propagator, right? So there will be fermion propagator S on xi. Roughly speaking, let's write that you will have S on xi and then multiply with some exponential, which in one case, I think it will contain P1 plus Q1 multiplied by xi. And in the second case, with the second exponent, it will contain S on xi exponential I P1 minus Q2 multiplied by xi. And so integrating over xi means that you will be coming to the Fourier transform to the propagator in the Fourier space, which we know very well what is this. And integration over eta will produce delta function, which turns out to be nothing else as a delta function describing the conservation of the total momentum. And so after you perform this trick with change of variables and integration, then the answer you get is the following: G squared 2c squared mc over h bar 2 pi 4 delta function, which comes from integration over eta, and over this variable eta only exponentials will depend, and so integrating you will get this conservation law. P2 plus Q2 should be equal to P1 plus Q1, exactly what you would expect from this matrix element, and cross the remaining expression, which involves the Fourier image of the fermionic propagator. So now this S, which I'm writing, depends on momentum because it's a propagator in the momentum space. Epsilon mu M2, Q2 epsilon M1 nu Q1 plus U bar S2P2 gamma mu S P1 minus Q2 and then what else is gamma nu, US1 P1 epsilon M1 mu Q1 epsilon M2 nu Q2. Now, once you get this expression, you can actually see that you can interpret it very nicely in a graphical way by using the Feynman rules, which I have introduced in the previous lecture. So you see that this answer for M consists of two terms, and each of these terms can be described by the corresponding Feynman diagram. So let's consider the first term, this one here. So this term can be graphically expressed in the following way. There is an incoming photon, which contains, which has momentum Q1 and the polarization M1. This is what is encoded in this epsilon here. And there is an initial electron which gets into the interaction vertex. It enters with momentum P1 and the polarization S1. This is described by this spinor US1 depending on P1. Then there is a propagator. That's depending on the momentum K equals to P1 plus Q1. So that's exactly sum of the momenta Q1 and P1 which enter the interaction vertex. The interaction vertex is weighted with the weight I gamma nu, Ig gamma nu. This is this gamma matrix. And Ig, I've taken Ig out of minus G squared. Then there is another interaction vertex, also weighted with minus Ig gamma mu this time. This corresponds to this gamma matrix here. And then out of this vertex, you see the electron coming out with momenta P2 and polarization S2, and the photon with momentum Q2 and polarization M2. So M here is an index, so this is polarization, so please don't confuse this with a mass. This is not a mass of a photon, but this is polarization index M1 and M2. And so this is exactly the Feynman diagram, which describes the contribution analytically expressed as U bar on P2, gamma mu S P1 plus Q1, gamma nu U S1 on P1, and then polarizations, epsilon mu M2 Q2, epsilon M1 nu Q1. Is it clear how I draw this diagram?
Yes.
Mm-hmm. Yeah, so up to this unessential prefactor MC over H bar, and the overall delta function, which describes the conservation law, overall conservation law, then this is a matrix element which you can put in correspondence with this graphical, nice graphical interpretation of scattering process. What about the second analytic expression, which also contributes to this diagram? By the way, this diagram is called S-channel diagram, but there is another channel, so another diagram, which is expressed in the following way.
Professor,
Which, yeah. Yeah.
In this diagram, the time is running vertically or horizontally.
The time is running from right to left.
Thank you.
From right to left. That is how it runs on this picture. But there is another diagram which is describing the second element very similarly. So photon comes in Q1 M1, again momentum and polarization, and there is an electron coming in with momentum P1, polarization S1. In between them there is a propagator which as you see now has a momentum for momentum K equal to P1 minus Q2. This is what corresponds to this S depending on P1 minus Q2. And after that, yes, so you have electron coming out, P2 S2, and another photon. Another photon coming out. Another photon coming out. Let's denote momentum like this. Q2 M2. Again, there is an with interaction vertex minus Ig gamma nu here and minus Ig gamma mu here. So this is exactly the vertices which stand in the interaction term, psi bar gamma mu psi with minus Ig. And then you clearly see what they describe. There is a fermionic current which travels through the vertex, and the vertex emits a photon. So that's exactly the type of interaction we put in our S matrix. And so the scattering process then is a sum of these two diagrams. Well, the second diagram here we put in correspondence with, maybe I write below this diagram, U bar S2 on P2, gamma mu S on P1 minus Q2, gamma nu U S1 on P1, and then again photon polarizations. So this means that in principle, if you understand how to build up these Feynman diagrams, then you can write the corresponding analytic expressions even without performing this work, which I have done. You can, in principle, write the corresponding analytic expressions, first drawing these Feynman graphs and getting this geometric, intuition about scattering process, or visualize the scattering process in terms of Feynman graphs, and then you write down the corresponding analytic expression. So this is the lowest order of perturbation theory. As you see, it's like in the Thomson effect, the amplitude gets proportional to G squared, there is GPS twice. There are no loops. So these diagrams, they have a name of tree diagrams from the word trees, because there are no loops. There are no loops, there are only trees here. So these are tree diagrams. And they describe the Compton scattering at the leading order of perturbation theory in the Coupling constant. So for the first diagram, the virtual electron, so electron which propagates in between these two vertices, it has k squared actually bigger than m squared, bigger than the mass of electron, right? That's because if you take a square, so what is k squared? K squared is a p1 plus q1 squared, right? And so if you open the square, you will get P1 squared, but by mass shell, P1 squared is equal to the mass of electron. And therefore you see that in this diagram, K squared is bigger than M squared. While in the second diagram, you can show that in fact here, K squared is less than M squared. And so these are two relevant processes which can happen. The particle which propagates in between the vertices in this graphical interpretation is an electron, a virtual electron, whose momentum can be either bigger than the moment of electron or less than the moment, mass is either bigger in the first diagram than the mass squared of electron or smaller than the mass squared of electron. And when we understand this, we can proceed with evaluating the scattering amplitude, and we just read off directly what is the scattering amplitude. We know that the scattering amplitude is an expression which we detect from the matrix element, from the connected part of the matrix element, and this is a connected part which we have computed by stripping off delta function, which describes an overall conservation law. And so the amplitude of initial to final state, I use the same expression as we used in scattering theory to compute cross-section. So the amplitude is given by the following expression: G squared 2IC squared MC over H bar epsilon M2 mu Q2 epsilon nu M1 Q1 U bar S2 P2, and then here I put a tensor. I denoted Q mu nu US1 P1, and this tensor encodes both Feynman diagrams, contribution of these two Feynman diagrams, this Q mu nu on P1, Q1 and P2 and Q2, I define as the following expression: P1 plus Q1 gamma nu plus gamma nu S on P1 minus Q2 gamma mu. It's simply sum of these two terms. Where I isolated or just sum up these two terms, which give me this tensor Q mu nu. This tensor Q mu nu, if you write it by substituting the explicit expression for the Feynman propagator of fermions in the momentum space, you find out that this expression is then the following: I over 2 gamma mu P1 crossed Q1 crossed, and you know what I'm writing by this cross. This is cross means gamma mu P mu. By definition, this is gamma mu P mu plus M mass gamma nu divided product P1 Q1 minus gamma nu P1 crossed minus Q1 Q2 crossed plus mass of electron gamma mu divided by P1 Q2. This is one of the possible presentations of this tensor Q mu nu. Please do this exercise. Just show that this can be written in this form, and you can also show the following. This is also an exercise to show that if you define now another tensor, which is the same as Q mu nu, but sandwiched in between our spinors, U on S1 P1, sorry, then this object actually satisfies the transversality to photon momenta. So if you take, this means that if you take Q2, oops, if you take Q2 mu and sum it up over index mu, then this will be equal to 0. It turns out that this is 0, and this is the same as you take Q1 mu and sum it also with this tensor Q mu. You will get 0. And this is consequence, these equations, I mean, they are satisfied due to the fact that these spinor amplitudes here, they satisfy Dirac equation. Satisfy Dirac equation. You remember these amplitudes, these are amplitudes constructed for the free Dirac equation, and they satisfy for this reason the Dirac equation. And as a consequence of that, you will see that this tensor I introduced is orthogonal to photon momenta. And this property we have already discussed. It can be considered as a consequence of gauge invariance, which consists in the fact that if I shift polarizations of photons by any amount of momentum, then this does not change the scattering amplitude. So contribution of longitudinal polarizations which are aligned in the direction of photon momentum, they do not influence the scattering amplitude. And this is, if you wish, again, manifestation of gauge invariance at the level of scattering amplitudes. And now, since we have this amplitude at our disposal, we can go on and compute the cross-section. We can apply now our knowledge about cross-section, yes, to compute this cross-section for the actual real process in quantum electrodynamics, like Compton scattering. So cross-section, that's the last point. Cross-section. So the most simple computation of the cross-section for this Compton scattering process is done in the rest frame of the initial electron. So in the frame where initial electron is at rest. Being at rest means that its momentum, its form momentum P1, is simply mass, and then spatial components are all equal to 0. So in this frame, our electron is not moving, and P0 component of P1 is simply M. Then we have the conservation law, which is given by our delta function. P1 plus Q1 is equal to P2 plus Q2. That's a conservation law for 4 momenta. It can be split into the conservation of energy. P10 plus Q10 is equal to P20 plus Q20. And the conservation of special momentum. Special momentum for P1 is 0, you see, because we are in the rest frame of the first electron. And then P2 plus Q2. So I split this for the conservation law conservation law for momenta to the conservation of energy and conservation of spatial momenta. Now, from the second equation here, we can get P2. So electron momentum, spatial momentum of electron after scattering. We see that it's simply given through this conservation law to the difference Q1 minus Q2. And if I now take this answer and use also the fact that I'm talking here about asymptotic momenta, it means that each of the asymptotic particles satisfies its dispersion relation. And so let's now take this into account. So P10 is simply a mass of our electron. Then there is Q10 energy of the initial photon is equal to P20. And P20, what is this? This is now P2 squared, which is Q1 minus Q2 squared, plus the m squared of our electron, and plus Q20. Right, so this is this conservation law now, which is written by taking into account this expression for P2 and the dispersion relation for an electron after scattering. Also, for photons, we know that the dispersion relation is Q0 is equal to modulus of Q, because photon is massless. So energy is a modulus of a special momentum. And this means that what we can do, we can open here the brackets. We can open here the square. And so what do we get in this case? We will get Q1 squared, Q1 squared plus Q2 squared, minus 2. Then I write modulus of Q1, modulus of Q2, multiplied by cosine of the angle between Q1 and Q2. So Q1 is incoming photon, momentum of incoming photon, Q2 is the momentum of outgoing photon, and the angle between them I denote by theta. And then each of these Q's I can replace by Q0. So this is Q01, other way around, Q10 squared plus Q20 squared minus 2 Q10 Q20 multiply with cosine theta. So then my equation takes the form m plus Q10 is equal to square root Q10 squared plus Q20 squared minus twice Q10 Q20 cosine theta plus m squared plus Q20. And so what do you see from here? You see that this is a closed equation, which allows me to express, say, Q20 via Q10. I can solve for Q20 and find it as a function of Q10 and this angle, cosine theta. So after some algebra, what you need to do, you need to put Q20 to the left, then take a square, write equation for Q20 and solve it. And when you do this manipulation, please do it yourself, you will find that Q20 is related to Q10 by the following formula. Mass Q10 and then mass plus Q10, 1 minus cosine theta. So this is a relation between energies of the incoming and outgoing photons and the angle and the scattering angle of photons. This is how it looks like. Now you can also introduce frequency of photons. So omega is energy divided by c. So Planck constant I put also, I restore it in a second. So this is frequency of the incoming photon. Analogously, you can define the frequency of outgoing photon. And now if you substitute these expressions if you replace Q's by frequencies, then and restore everywhere speed of light and h bar, then you will get the following formula. Frequency of the outgoing photon is related to the frequency of the incoming photon by the following formula. 1 plus h bar omega divided by mc squared, 1 minus cosine theta. This is how it looks like.
Sorry, so previously you have excluded H cross and C.
Yes. Now I'm just restoring them, and this is a way. Yes, so h bar c with all the physical constants to be restored. You can see that this is what is needed in order to get the correct physical dimensions. H bar omega here, it has a dimension of energy. MC squared has a dimension of energy, so their ratio is dimensionless. It's multiplied by dimensionless quantity 1 minus cosine theta. And this is a relation between the frequencies of the incoming and outgoing photons. If you go on and rewrite this also in terms of wavelengths, so wavelengths lambda is introduced as 2 pi omega multiplied by speed of light, then this formula can be rewritten as this is a wavelength of the outgoing photon, and according to this formula, it will be related to the wavelengths of the incoming photon by the formula lambda plus 2 pi lambda Compton 1 minus cosine theta, where lambda Compton is nothing as we introduced before, h bar divided by mc, and this is the origin of this notation. So lambda Compton is h bar divided by mc. It comes from the Compton scattering through this formula, which relates the wavelengths of the incoming photon with the wavelengths of the outgoing photon. And what is interesting that you see from this formula, then the wavelength of the outgoing photon is always bigger than the wavelength of the incoming photon. So to the length of the incoming photon, you add up some positive number, because cosine theta is less than 1. And this means that a scattered photon is always left shifted. Its wavelength is bigger with respect, it's red shifted with respect to the incoming photon. Okay, that's probably from the physical point of view is very natural, because the photon loses part of its energy. It gives parts of its energy to electron with which it collides. And then this is a classical formula which describes the change of the wavelengths. And you see it's solely based on the conservation law of energy and momentum, and on the dispersion relations for electron and for a photon. So it's a classical formula which describes this wavelength shift. Okay, is it the derivation of this formula is clear? That's an important formula in the Compton effect. And now, yeah.
So I have a question about this. So
Yeah.
this relation between the frequency of photons have nothing, so far it has nothing to do with the scatter amplitude, right?
No, it has something to do with simply satisfaction by the satisfaction of the conservation law. And what the scattering amplitude will be, we are now going to discuss. We're actually going to compute cross-section. But cross-section, yeah, you will see. You will see.
Okay.
No, it has nothing to do with, for the moment, it has nothing to do with scattering amplitude. It's purely kinematics, which I'm describing here. for the moment,
Mhm.
and it's purely
Mhm.
based on conservation law.
Mhm.
And scattering
Thank you.
amplitude gives you, how to say, it gives you a number which will be related to the intensity of these internal interactions of photons with electrons. This is something microscopic. That's something which comes from the microscopic Lagrangian, but at the end results in the experimentally observed quantity, in the quantity which we observe at sort of quite large distances. We observe the effect of this, how to say, microscopic interactions which happen at the microscopic level in a small region of space and time. We observe it on large distances in our devices, which fix the results of the experiments and which show up in this theoretical quantity, which we call cross-section. Now, we know that one of the constituents of the cross-section is the Lorentz invariant phase space measure. And now we need to compute it in the rest frame of the initial electron. And it's computed with our general formula. I'm not going to repeat it here, but you can have a look back to our lecture on scattering. And but there we needed to compute this Lorentz invariant phase space measure. We needed to evaluate such a quantity where K03 and K04 was they were energies of two outgoing particles. In the case when in the final state we have two particles, and we do have two particles. One of them is an outgoing photon, so K03 coincides with an energy of the outgoing photon, and the other is outgoing electron, so K04 I identify with the energy of the outgoing photon. And this is according to the conservation law here. P20 is P10, which is M, plus Q10 minus Q20. So according to the conservation law, this is mass plus Q10 minus Q20. And rho here, the quantity over which we differentiate. If you go on to look at our construction of the Lorentz invariant phase space, is K3 modulus of it. That's where we introduce this spherical coordinate system. So modulus of spatial momenta for an outgoing photon. But for an outgoing photon, since it is a photon, due to its dispersion relation, it just coincides with Q20, because it's a photon. Therefore, we can go on and just integrate, and just differentiate. So if you allow me to continue this expression here, what I have to do, I have to differentiate K03, K04 over K20. And I do it in the following way. So K20 over K20, the first term gives me 1. But in the second term, I have to take into account that due to this conservation law, let me see, I'll first write and then make a comment. I need to differentiate the following expression: square root of Q10 squared plus Q20 squared, like this, minus twice Q01, Q02, plus M squared. Because this expression is, as you see, it just follows from here. M plus Q10 minus Q20 is this square root, according to the conservation law. And if I perform this differentiation, then I obtain here nothing else as 1 differentiating square root. I will get square root in the denominator. Like this, and differentiation over of the expression under the square root over Q20 produce Q20 Q20 minus Q10 cosine theta, right? And then I replace the square root back by this expression M plus Q10 minus Q20 to simplify it. So I will get 1 plus Q20 minus Q10 cosine theta. And here M 10 minus Q20. So at the end, if you make common denominator, then this becomes M difference of photon energies, and here M plus Q10 1 minus cosine theta. This is the expression which you have. For this quantity, and this quantity is a part of the ellipse, Lorentz invariant phase space differential. I just now take an expression which we have derived in the previous lectures. For this ellipse, remember 16 pi squared c squared, then momentum of the outgoing electron, which is in terms of photon momenta is written in this way. And then in the denominator, there stands this expression we have just computed. So I substitute M plus Q10 1 minus cosine theta divided by M plus Q10 minus Q20, which shows me then, sorry, I forgot also to write Q20 here, which shows me that actually there is a nice cancellation of these two terms. And then the resulting expression can be written in the following way. Again, if you look at this formula here, it shows you that the product of Q20 by M plus Q10 1 minus cosine theta is simply MQ10. And so this expression which you observe in the denominator, Q20 multiplied by this expression, you can simply replace by Q10. And so your formula then takes a super simple form: energy squared of the outgoing photon divided by mass energy of the incoming photon. No, and then there is this prefactor 16 pi squared over c squared. So this is the ellipse. This is the ellipse. And finally, we write d sigma, our cross section. This is combination of the ellipse with a scattering amplitude. So 4c squared M Q10, and then sorry, yeah, I have to start from the scattering amplitude probably. Let's start from the scattering amplitude. AFI squared, modulus squared, and then there are prefactors coming from the contribution of initial particles. So the ellipse comes the last. And then if we substitute this d ellipse, then we obtain the following nice formula. Q20 over Q10 squared multiplied by modulus IFI, square of the amplitude, d omega, and then 64, 4 multiplied by 16. There, pi squared, c in the power 4, m squared. This is how the sigma looks like. You know that the ratio of this Q20 to Q10 can be expressed via frequencies of the incoming and outgoing photons. And if we are also interested in the scattering of unpolarized electrons, but keep polarization of photons, then we have to sum over polarizations S1 and S2 and divide the result by 2, which means averaging of the polarizations of incoming photons. And so differential cross-section, this sigma over d omega, is then given by the ratio of Q20 to Q10. You are taken from this formula. So Q20 to Q10 is the same as the ratio of omega prime to omega. So omega prime divided by omega squared multiplied with 1 divided by 64 pi squared C4m squared. And then, as I said, if you are interested in unpolarized electrons, you are summing over S1 and S2. This square of the amplitude, and you divide the result by 2. And so if you substitute now the expression for the amplitude here in this expression, then you see that this becomes 1 over 2 g squared divided by 4 pi squared. Is it really a square here? I doubt it a little bit that it's square. It's probably there is no square. G squared over 4 pi, and then there is what happens is that there is omega prime over omega squared, and then there is a expression J, where J encodes all the remaining information on photon polarizations. M1 Q1 epsilon rho M2 on Q1, epsilon M2 mu on Q2, epsilon sigma M2 on Q2. No, this is correct what I'm writing. Actually, here is square. That's because you are taking a square of the amplitude. So amplitude itself is proportional to G squared, but you're taking modulus squared of it. And that's why you need to square G square square. That's the reason why it appears there. And cross sum over polarizations S1 and S2, U bar S2, P2, Q mu. That's a tensor which I have introduced. The one which contains the Feynman propagator for fermions, U bar S1 P1, Q bar sigma rho, and then U S2 P2. Quite complicated expression. Now, this is the most probably technically complicated part, which comes from the fact that you take a modulus of the amplitude square. That's why there appears so many terms here. You see you have 4 polarizations. You have also a lot of spinors, and now the question is how to compute this quantity. So this is actually the technical story, which you can look in my lecture notes how to do it. The final, the outcome of the computation of this complicated expression is at the end rather simple. So I just give the final formula. The sigma over d omega is alpha squared divided by 4m squared. I will tell you what is alpha squared. So alpha is a fine structure constant, omega prime over omega squared, and then omega prime over omega plus omega divided by omega prime plus 4 epsilon m1 epsilon m2. So this is a product of polarizations of incoming and outgoing photons minus 2. Here alpha is a fine structure constant, and one can also introduce what is called classical radius of electron. This is a ratio of a fine structure constant to the electron mass, and written down with all the constant restored. This is E squared divided by 4 pi mc squared. And this quantity is approximately 2.8 10 to the power minus 15 meters. So this quantity is called the classical radius of electron. And this is a quantity which would arise from an assumption that the rest mass of electron is totally due to its own electrostatic energy. So mass mc squared of electron is due to its electrostatic energy, E squared divided by the classical radius of electron. And this quantity, in fact, enters this formula here. This formula, by the way, it has a name. It's called Klein Nishina formula, by the names of people who derive it. So Klein Nishina formula. And it describes the cross-section of the Compton scattering. Now, for small energies of the initial photon, h bar omega tends to 0. Then in this situation, omega prime is almost the same as omega. So the energy which goes into electron is very small. So photon has not enough energy. So it just has little energy. And this means that if you look at the formula how omega related to omega prime, then you will see that with a little energy, omega prime is almost equal to omega, because this term becomes very small, because omega is small, and then omega prime is approximately equal to omega. And in this situation, you see ratios of omega prime to omega can be replaced by 1. In this case, these two terms cancel with this 2. And then the formula for d sigma over d omega goes into, when omega goes to 0, goes to alpha squared divided by m squared, epsilon m1, polarization of photons. These are 4 vectors, so and index mu is summed up for epsilons. And so this is, in fact, in this limit, the sigma over d omega goes into cross-section of the Thomson scattering. So this is cross-section of the Thomson scattering. And as you see from this formula, this is proportional to the classical radius of electron squared. So if you do squaring, then you see that this is approximately 10 to the power minus 30 meters squared. So it's a very small cross section, very small quantity. And that's why in particle physics, one adopts a special area scale to measure the cross section, which is called barn. So cross sections are measured in barns, and one barn is approximately, or it's equal, it's taken to be equal to 10 to the power minus 28 meters squared. So, right. So this is how the answer for the cross section looks like. Where in fact, if you are not interested even in the polarization of photons, incoming and outgoing, you can just sum up over these polarizations and divide the result by 2. And in that case, this sum you can show explicitly. Look at my lecture notes. That this quantity, product of polarizations, sum up over polarizations, is simply 1 plus cosine squared theta, where again theta is an angle between incoming and outgoing photon. And so when you substitute it into this formula, then what you get is the following expression: d sigma over d omega is equal to classical electron radius squared over 2. And classical electron radius, this is, as I said, this is alpha divided by m. So classical electron squared over 2, omega prime over omega squared, omega prime over omega plus omega divided by omega prime minus sine squared theta. No, and finally, if you want to compute the full cross section, sigma, then you need to integrate over a solid angle this expression. And that gives you the following. So you need to take integral from 0 to 2 pi in the angle d phi, and also integrate theta, sine theta d theta. This is a measure of a solid angle. And the resulting expression you can write in terms of a quantity gamma, which is h bar omega divided by mc squared. So ratio of energy of incoming photon to the rest mass of the electron. And then this expression, which you have to integrate in terms of gamma, is written in the following way. So this is gamma 1 minus cosine theta squared. And here there will be 1 divided by 1 plus gamma cosine, 1 minus cosine theta, 1 minus cosine theta, plus 1 plus gamma 1 minus cosine theta minus sine squared theta. And quite surprisingly, you can compute this integral in terms of elementary functions. So sigma upon integration gives you the following nice answer. This is PR electron squared, 4 divided by gamma squared, plus twice 1 plus gamma. You can check me. This is, if you put this expression into Mathematica, it will integrate for you in terms of elementary functions. And this is how the answer then looks like. And this is the answer for the total cross-section of the Compton scattering. So this answer depends on the energy of the initial photon through gamma. Gamma, this is where the energy of the initial photon comes in. It's proportional to the classical electron radius squared. And expanding this right-hand side in powers of gamma, you should not look like gamma here in the denominator, but this expression here does not have any singularity. It has a nice expansion in powers of gamma. So if you expand it in powers of gamma, then it goes in the following way. So pi r electron squared, and then you get 8/3 minus 16/3 gamma plus 208/15 gamma squared minus 532/15 gamma cubed, and so on. So in fact, expansion in gamma, you can consider either as an expansion in terms of frequency or energy of incoming photon, or the same as an expansion in powers of h bar. And the first term here is purely classical. It gives the total cross-section of Thomson scattering, which can be found just by using the methods of classical electrodynamics. So this is formula. The first one is Thomson. Thomson total cross-section, and then there are corrections to it coming through quantum field theory, corrections in h-bar. So with this, I would like to finish this explicit example of computing the scattering matrix in quantum electrodynamics. Of course, as I said, there are other interesting processes, but armed with this knowledge of how these scattering processes can be computed, you can now do this kind of at least 3-level computations yourself. Okay, then I propose to make now a 10 minutes break, and we continue with some other topic in quantum field theory. Okay?
Professor.
Yeah.
So this cross section means that the amount of area that our light has interacted on, right?
Yeah, effectively, if you think about the classical picture, then yes, this is essentially concerns basically the area where the scattering is effective, where say photons and electrons undergo scattering, and so this is computed in the rest frame of the incoming electron. But we know that since sigma is Lorentz invariant quantity, then this answer should persist in any Lorentz frame.
Yes, so here sigma is Lorentz invariant quantity.
Yes, it's Lorentz invariant quantity. You see, it depends on a frequency of a photon only. No, and frequency of a photon is a photon energy. What else should be said? It also depends on this quantity, which is a classical radius of electron. Yeah.
So this formula tells us that it is invariant of the frequency we use.
That's right. Yeah.
Yes.
You see, even what is interesting is that the Thomson total cross-section does not depend on anything. It's just classical electron squared. So the answer depends only on the electric charge and on the mass of electron.
Yeah.
Further corrections, you can say that the corrections coming from quantum effects, quantum field theory,
Yes.
which make difference between classical electrodynamics and sort of quantum electrodynamics. Right. And of course, you can also write gamma if you wish in terms of Compton wavelengths. So if you think about gamma in this way. So we say it's h bar omega divided by mc squared, but this I can split and write in the following way: omega over c divided by mc over h bar, right? And this then is a wavelength of incoming photon divided by lambda Compton. Divided by lambda Compton. And so you see that gamma is small if lambda is much less than lambda Compton. And so when lambda becomes comparable to lambda Compton, it means that effects of quantum field theory are not anymore negligible. So when the wavelength of the incoming photon becomes sort of comparable to the Compton wavelength, gamma is not anymore small, and so quantum corrections become visible, very visible.
Yes, in higher energy, have some correction.
Yeah. That's right. I think I did kind of, sorry, I think I said something wrong here. It's other way around. That's why I'm looking at this formula and puzzling myself a bit, sorry. It's other way around. It's lambda
Inverse.
Compton divided by lambda, yes.
Yes, it should be inverse.
That's right. I'm looking at this formula and puzzling myself. It's lambda Compton divided by lambda, because lambda is C over omega, if you wish. Yeah, it's other way around. Of course. So when lambda much bigger lambda Compton, then gamma lambda bigger lambda Compton. So lambda, big lambda means that it's a kind of infrared photon. It has a large wavelength. Small energy, large wavelengths. So if lambda much bigger than lambda Compton, then gamma goes to zero and quantum effects are negligible. When we have other inequality, and so lambda is comparable to lambda Compton, then gamma is not small, and quantum effects become dominating. Yeah, then this is correct what I said now.